For thousands of years, this star, Polaris, the North Star, has been humanity's unwavering guide. But what if I told you that this icon of steadiness is, in reality, one of the greatest mysteries in our galaxy? That the closer we look at it with our most powerful instruments, the less it makes sense? How can a star we've known for millennia be so evasive to our billion-dollar telescopes and satellites? It's deeply ironic, isn't it? This isn't just about one star. Polaris is a key, a master key, to measuring the entire universe. The secrets it's hiding could force us to redraw our map of the cosmos. In 1779, William Herschel saw something no one had ever seen before, a faint companion star. He discovered the first secret. Polaris wasn't alone. Polaris A was wobbling. Its light was being stretched and compressed, suggesting an invisible dance partner, a spectroscopic ghost. It took until 2006 for the Hubble Space Telescope to finally take its picture. The North Star wasn't a duo, it was a trio. So let's meet the family. This is a hierarchical triple system, a cosmic matryoshka doll of gravity. If you could plop this thing in the center of our solar system, its searing surface would stretch more than halfway to Mercury. Polaris B orbits 24 times further out than Voyager 1. Its journey is a lonely, glacial trek that takes 40,000 years. The shift is infinitesimal, equivalent to viewing a single coin from a distance of over 3,000 miles. The model suggests Polaris A is a youthful 50 million years old, but its distant sibling appears to be an ancient 2 billion years old. Henrietta Swan Leavitt found something remarkable: a direct relationship between how long a Cepheid pulsed and how bright it truly was. Astronomers had a standard candle. If you knew its true power, you could calculate its distance precisely. This single law built a critical rung on the cosmic distance ladder, the foundation we use to measure the entire universe. For decades, the difference between its bright and dim phases shrank almost to nothing, as if the star was calming down. For over a century, its pulse has been slowing down. Then, just a few years ago, it reversed. It started speeding up. The Hubble Tension. When we measure using the distance ladder, we get 73, but when we use the afterglow of the Big Bang, we get 67. If our nearest calibrator, Polaris, is behaving in ways we don't understand, that crack might start right here. The prevailing theory is that Polaris is transitioning between instability phases, a brief, poorly understood first phase that lasts only tens of thousands of years. Observations detected giant star spots on its surface, indicative of strong magnetic activity that could alter its evolution. Another hypothesis is that Polaris is shedding mass at a tremendous rate through a powerful stellar wind.